Good morning, ladies and gentlemen. I'm sorry we had to cut down the tea time today. It was a great session that we had in the morning, very informative, and I think a lot of passion flowed too, and which was a very important indicator as to how much of energy the industry is also trying to put in to support the defense services in our defense capabilities focused on space. Uh, Now we are going to start with the first of the panel discussions. The topic is persistent and resilient space for ISR capability. Uh, Keeping the challenges of time in mind, we request all speakers to please limit your talk to 5 minutes strictly. And we will also be ensuring that we do not read the biodata because that will consume 1 minute, and it's more important to listen to the material that is there rather than the biodata. So, with your permission, sir, I can take that liberty, sir. May I please request our head of the panel, A Vice Marshal PV Shivanand VM, ACS Ops AD, to please come. Uh, Group Captain P. Chandrasekhar, he is Group Captain IMINT Air Headquarters. Captain Jasneet Sachdeva, Captain NCO. Mr. Awais Ahmed, Pixel. Mr. Navneet Singh, Kepler Aero. Air Commodore A. Baduni, Commandant IPAC. Mr. Aaron Van Maxar, and I shall be the moderator. I'll now request AVM Shivanand to please introduce the topic, and I shall be the moderator conducting the question answer session in the end. Thank you.
Good morning, everybody. I would like to take this opportunity to thank the organizers, Geospatial World and the Indian Space Association, for getting together the industry, the technologists, the consumer at this magnificent venue to share their thoughts and take space exploitation into the next higher orbital plane. The topic for this panel discussion is very relevant today. What with the pervasive dependence on space-based sensors being the new norm. Space is the ultimate high ground, and to emphasize this subject and this aspect, I would like to take a small anecdote from my own life and recount it just to add a little bit of flavor to this occasion. Well, I will take you back to the late 1980s, early 1990s, when I was inducted into one of the fighter squadrons in the Western sector. And life was all about not getting shot down in the first 1 minute of an air combat training mission. And when air combat revolved around eyeball Mach 1, and navigation was all about the moving thumb display. After several futile missions, when I was just unable to make do the objective, I approached one of the senior pilots in the squadron and asked him how does he manage to stay unscathed. His advice was simple. He said, "Boy, just perch up and see the view." From then on, this altitude differential of a few thousand meters brought about a transformational change in my own situational awareness in a combat training mission. Today, the space domain is all about the God's eye view, and its exploitation sets the pace for complete battlefield transparency. I'm indeed privileged to be amidst a very bevy of specialists in the space domain who would cover varied topics today in this panel discussion. Increased need for quick and precise responses call for a shortened sensor to shooter loop. With increasing ISR inputs coming in from space, there is a need to find a solution to enable this. The second panelist will cover the aspects of the ISR specific to the maritime domain. This domain presents unique challenges and opportunities. Disruptive technology can address several long-standing challenges in the ISR domain, and exploitation of the hyperspectral imagery is one such avenue. Space situational awareness is very close to my heart, and with space now being increasingly contested, there is a clear and present need to understand and implement a robust SSA. And lastly, the ISR solution and integrated battle space, both in terms of product deliverables as well as for decision making, will be the last two aspects that will be covered in today's discussion. Without much ado, I now hand over to the first speaker who would cover the topic on sensor to shooter loop.
Good morning, ladies and gentlemen. I'm Group Captain Chandrasekhar. In my assigned 5 minutes, my essential talk is only to the industry. And I now realize will be a repetition of some of the points that two of the industry panelists from the first panel covered. So quickly I realized that we have the technologies available. We perhaps do not have the interface with the military. In any sensor shooter loop, I will be covering this under the following heads, where I'll initially touch upon the limitations of exploiting ISR exclusively from space, and like I just preluded, what the solutions we seek from the industry. These are the 4 essential issues I find with respect to limitations of space-based ISR exploitation. Please note that I have assumed that the sensor is as is, where is, and so is the shooter. With respect to the SATCOM downlink time, I understand that this cannot be implemented on an existing satellite. Obviously, this is for you in the industry to look forward or to predict in the future satellites that come up. However, the remaining 3 bulleted points in processing and dissemination, decision making, and info flow to C2 to shooter are invariably very closely intermeshed. Coming to the solutions we seek from you. Like I covered, these are not solutions you can implement now on existing satellites, I understand that. But definitely high bandwidth downlinks, laser communication, as well as intersatellite links will significantly overcome some of the defense issues in terms of getting information down from satellites. This is the crux of the matter. And like I just covered, I understand that we have expertise within our industry on this. So with ISpA driving the interface between the policy, the government, the industry, and the military, I think these solutions can perhaps be implemented within days, on a worst case scenario, maybe within months. So we look at faster image processing. AI seems to be the buzzword for almost any application. Smart onboard processing to the limited extent as it stands. I am seized of the limitations in terms of power generation and management, and therefore its implementation in terms of absolute smart processing on board, which is not required. So perhaps just a cloud detection rejection circuit on board and a split-based processing on ground will give us what we want. Multi-sensor fusion and multi-domain fusion, DG-DSA covered. So we want inputs from different sensors, say SAR, ELINT, and EOIR to be fused. We also want non-sensor-based information, say from human, from OSINT, from Twitter feeds to be fused in a layered manner. Obviously, all this is towards giving the composite air picture, operational picture, as present-day GIS delivers this, and therefore I am leading it with the word manageable. All GIS solutions are manageable. This manageable refers to manageable across the 3 services to their specific requirements. In the other 2 solutions that we are looking at, decision making will flow out of what you give us in my subpoint 3, where the system can throw up some automated solutions and some automated responses. Obviously, the man in the loop will take the final decision. And the last 2 subpoints, how the information reaches the shooter needs no deliberation. So I'll quickly conclude to say, where can the industry give the military breakthroughs? In software, processing power, and data management. The aspects of data management I have enlisted there. However, with specificities of space, what you can give us, maybe in a shortened time frame, are intersatellite links, totally removing the ubiquity of the satellite pass and it's being tied down to a ground station and the visibility times. Power generation and management towards a smarter, say, 3-split processing, either on board, at the receiving end, and at the decision maker's end. Propulsion and enhanced maneuverability do not necessarily shorten the sensor shooter route directly. What it enables us is to deploy the platform on a faster image capturing process rather than use it either in trail or wait for it to make its second pass. I thank you for your time. Just the overarching ambit remains that all this has to be happening in terms of a secure cyber environment. Thank you. Jai Hind.
Good morning, ladies and gentlemen. Firstly, at the outset, I would like to thank General Bhatt and the chair for this session, AVM Shivanand, and the distinguished panelists who are co-chairing this session. And it is indeed a privilege and an honor for me to be here and speak to you in the next 5 minutes on how the Navy looks at the space-based ISR for MDA. The scope of the presentation is as shown. I'll quickly jump to the business end of my talk. But before I continue, I would like to just give you a brief perspective of what do we understand by the maritime domain. The International Maritime Organization defines MDA as the effective understanding of anything associated with the maritime domain that could impact the security, safety, economy, or the environment. So these 4 are the key words: security, safety, economy, or the environment. So anything that impacts is in the maritime domain is related to MDA. And contrary to the normal understanding that we have, that maritime domain is restricted only to the surface of water, that is not so. It is, in fact, all-encompassing: surface, subsurface, and also the air dimension that is above this maritime domain. So all these 3 distinct dimensions also form part of the MDA. Also, I'm very sure that you are generally aware of what are the challenges in the maritime domain, from maritime terrorism to natural disasters to piracy, robbery, illegal, unreported and unregulated fishing, drug smuggling, gun running. So all these are generally known. So I'll not dwell upon this. But importantly, the point that needs to be highlighted is that MDA is a key enabler for combating these challenges. As per the data available with the Indian Navy's Information Fusion Center, Indian Ocean region, which is situated at Gurugram, we monitor about 15,000 vessels daily only in the Indian Ocean region. And on an annual basis, this contributes to nearly about 33% of the bulk cargo, 50% of the global container traffic, and 66% of the global oil traffic. And this, in addition, we have about 500,000 fishing vessels which operate in this area. And there are a large number of warships of extra-regional navies that too operate in this area. But this does not include the dark vessels which do not transmit on AIS, which is a big challenge and which I'll be dwelling upon a little more in detail. In the shore-based sensors, we presently use AIS, synthetic aperture radars, over-the-horizon radars, electrico-optical systems. But all this, even if augmented by ships and aircraft, they have limited surveillance coverage. And these are inadequate for developing the desired level of domain awareness. On the other hand, we have the space-based sensor technologies, such as the space-based AIS, the space-based automatic dependent surveillance broadcast, which enable persistent monitoring of the maritime domain in the surface and the air dimensions. But these services, presently we do not have indigenous capabilities, and these come at a very, very high premium cost. In the subsurface dimension also, the satellites are increasingly being used in conjunction with pre-deployed and widely dispersed surface and underwater buoys based on static sensors to not only detect underwater vessels, but also to study the oceans. Therefore, we can see that the space-based assets and applications already form a vital component of efforts to build the necessary awareness in all 3 dimensions of the maritime domain.
Now, coming to the future perspective, I'll briefly touch upon certain emerging trends and technologies. Coming to trends first, the users these days are more inclined to buy solutions rather than assets, and so is the Navy. And the second thing is about the small and transient satellites, which we look at to be launched on demand and purpose for specific operational tasks at extremely short notice. And this notice could be in future maybe a few hours. So undoubtedly, there are a whole lot of advantages of such models for meeting our space-based MDA requirements, and most important being the significantly reduced investment costs. Talking of emerging space-based technologies for MDA, the latest and the most promising emerging technology is the radio frequency detection. I would like to develop on this a little more in detail. The automated vessel monitoring and behavioral detection, which significantly minimize the time and resources needed to identify vessels engaged in suspicious behavior. And today, the biggest challenge in MDA, as I spoke of earlier, is locating dark vessels. That is, vessels which do not transmit on AIS, either for genuine operational reasons or illegitimately for nefarious activities. And I'm sure all of us can fathom the challenges of which are akin to finding a needle in a haystack. And it is for such situations that satellite-based RF signal geolocations of navigational radars and communication signals can significantly enhance dark ship detection. More importantly, the RF geolocation solutions, when correlated and fused with electro-optical imagery and global AIS data, could prove invaluable in filling these AIS gaps. And as far as maritime law enforcement agencies are concerned, such inputs could provide insight into potentially illicit activities such as IUU fishing, piracy, trafficking, and smuggling, and thus providing much more confidence before deploying costly resources for surveillance and reconnaissance. The armed forces are not the only benefactors of these emerging and niche technologies, as has been alluded to by the previous speakers as well. While the chain detection methodology in synthetic aperture radar satellites helps in tracking satellites and aircraft over sea and fulfills the surveillance and reconnaissance requirements, the same technology is being used now to assess the rising sea levels, receding coastlines, the impact of floods, and how the associated insurance claims are cleared. Similarly, the need for secure, safe, and reliable communications with minimal interference from cyber attacks is a basic requirement that one can ill afford to neglect. These facts therefore clearly indicate that once imbibed and embedded in our commercial space ecosystem, any new space-based technology will definitely have immense dual-use potential. The large amount of data that has been generated by these sensor platforms comes with a concomitant problem that the human analyst would not be able to effectively search for targets without artificial intelligence and machine learning based algorithms. Although the algorithms behind these automated target recognition tools are only as good as they are trained to detect the targets. Further, we cannot remain oblivious to the fact that the day is not far when we'll have technologies to trick these AI/ML enabled systems, not by changing the digital data, but by making physical changes in the real world. I'm sure some of us would have heard how researchers have successfully modified the stop signs to appear as speed limit signs for Tesla cars. And even glasses and shirts have been created to fool facial recognition algorithms that may be running on public surveillance cameras. So the day is not far when such technologies with minor modifications on board hulls, on board vessels, could actually be aimed at tricking these AI and ML algorithms that we are all building today and incorporating in our future satellites. So as these technologies evolve, so will the deception techniques too will evolve, and it would be a continuous race to catch up. Talking of disruptive technologies, I would like to mention about one technology that is going to completely revolutionize the landscape of space-based ISR and would be a competitor definitely for near space operations. That is the high-altitude pseudo-satellite. These unmanned stratospheric solar-powered vehicles could provide versatile ISR options, thereby obviating the limitations of conventional satellites. Low in cost, easier to launch, with the option to reuse and reconfigure the payloads. These can be used for persistent monitoring in a specific area of maritime interest as well as provide communication and internet connectivity over far-flung islands and mid-oceanic regions. The applications are endless. Lastly, on this particular slide, I have just listed down a few pointers for the industry, which I'll not dwell upon. And most of these have already been covered in the morning session as well. And to conclude, I would like to summarize that despite many challenges in the field of space-based technologies, the government's in recent initiatives are significant steps in the direction to create a vibrant space ecosystem. And I'm sure that the deliberations of this conference and the collective wisdom of all who are present here would bring in consolidation of ideas and convergence of thoughts, which would be of immense importance and would form key takeaways for all of us to focus and carry forward from here. With this, I have finished. Thank you and Jai Hind.
Good afternoon, ladies and gentlemen. I'm Ekamodo Baduni. I'm Commandant at DIPAC. The essential strategic overview for AI in ISR has already been given by the speakers in the morning session, and therefore I'll be dragging you into the operational aspects of this particular thing during the course of my presentation. Now, AI is something that is bandied around pretty loosely, as we have learnt over a period of time. There is a grey zone between AI, ML and what is generally a normal computer algorithm. Therefore, I will not be specific as to what merely the AI solution is. I just want to give a generic overview of what needs to be taken into the machine learning domain or the AI domains for assisting us in dealing with the AI in the space of ISR. Okay. I will restrict my scope to the IMINT cycle, that is at the operational and the tactical level. This is the nuts and bolts of what is required and the factors that go into factors that you need to look at while dealing or making an algorithm that deals with the AI ML software. Now, the first of the aspects that is there is payload planning. Now, this is an art and not a pure science. This is something that needs to be looked at by the AI developers, primarily because you have multiple agencies giving in their demands for an area that is in close proximity, which means an area which is just about 100 kilometer by 100 kilometers, you might have 20 people demanding 20 different targets within this area. Now, these have connotation for people who are in the satellite business to understand that the maneuverability of the satellite and the amount of images that can be clicked are restricted. At the end of the day, a satellite is moving at almost 7 kilometers a second, and therefore your time available over the area is limited at best. The prioritization level between these agencies is another aspect. Trust me, no agency believes that its priority is lower than the other user. That prioritization is an important aspect and needs to be factored in. There are specific sensor requirements for each agency for a particular area. So you have duality of demands. The same target would be demanded by a person who wants to see it in the SAR domain, on the EO domain, and today even in the hyperspectral domains. They have to be balanced. The currency and periodicity of demands varies widely. Some user may want a particular target to be done in 6-monthly periodicity, and the others may want it on a weekly periodicity. This has to be balanced with the overall capability that exists, since the amount of assets available will always be short of what is required. The queuing input that most of the AIs need to look in before an area for imaging for payload planning is decided is in the field of the data that is coming from OSINT, COMENT, SIGINT, ELENT, HUMINT, which is generally well understood for factoring into planning. Over and above, weather is an important factor. The payload planner needs to know in advance whether if he is planned, for example, an EO satellite over a particular region and it's likely to be cloudy on that particular day of planning, he should get an option of somebody indicating to him that a SAR or a different target might be taken rather than waste the effort that is there. The maximum utilization of resources and prioritization of demands are actually sort of an oxymoron. Given the fact that let's say for a particular area, you could image 5 targets, and you have a set of targets that are aligned. There are 5 targets. One is almost in the axis in which you can image in one go, and all those have a priority of let's say 8 out of 10. So you get 4 targets in a single pass. However, there is one target which is off the nadir, and that particular target has a priority of 9. So who gets preference? Does optimization get a preference, or should prioritization be given the preference? It's a matter that brings this entire payload planning into the realm of an art, and therefore AI is essential for us. The availability of alternate resources to be factored is essential. For example, I do the payload planning for a certain set of satellites. I need to be able to get the data and the inputs from what is commercially available and can support or maximize my efforts. The next basic stage is of image processing. This is a stage where the challenges basically have already been commented upon by some of the speakers are on the area of image fusion. However, here we are not talking about an image size of 5 by 5 kilometers. We are talking about very wide area image fusion capability to give you a pan-sharpened, natural colored images. It has issues of GSPs or tie points not being available, being hidden under clouds, and therefore the image is not working out the way we want it to be. However, the AI can assist us by making artificial GSPs or tie points to better integrate the entire spectral bands that are available for exploitation for a particular image that is there. The EO and SAR, while the image fusion between these two for specially change detection is an essential issue, however, the challenge comes from the temporal difference. And this temporal difference is not merely, cannot be merely addressed by sensor fusion. It is a deliberate temporal difference that we would want for reasons of operational necessity. However, this temporal difference means that fusing these types of images is a very big challenge that cannot be addressed purely by software, which is not in the realm of AI, genuinely in the realm of AI. So a similar problem statement pertains to the HISES hyperspectral images as well as the EO image fusion, given their vast difference in the spatial resolution. Therefore, to extract a meaningful data set out of it, you need to be able to bridge this difference. Obviously, enhancing the speed of multiple products. The data sets remain common. However, the amount of products that can be generated out of that same data set is enormous. Being able to provide that product to the right user at a faster speed is of essence. Now we come on to the glamour end of AI, which is the image analysis. On this, I will not take too much of time. The detection, identification, classification, and the change detection based on object of interest is something that is addressed by enough number of people who are present in the hall. Okay. The challenge lies here. We want to be able to do this in a very wide swath imagery with low resolution and dealing with small targets. This is where the operational and tactical int is extracted from. Okay. We need for the images to be able to be context based. Lack of time, I would not like to delve into the details of what context means. However, we can discuss this subsequently. Aim is to identify target behavior patterns on a wide area. Till now, what we have talked about is merely data extraction from a wide amount of or a voluminous amount of data that is available. The intelligence starts from this point. To be able to get the target pattern behavior and therefore make a predictive model and therefore give the decision makers the options that was talked about in the morning session. Correlation of data in the image with other sources of intelligence, that is the LINT inputs, the comment inputs, the OSINT inputs, etc., which feeds back to the payload planning cycle. Correlation of data for queuing for the next cycle of planning becomes the essence, and correlation of inputs with the archived image. And this is not what I am talking about is a time series analysis. I am talking about correlation with the archived image of what is available in that particular image for the image analyst to be indicated on what other data to look at for drawing a conclusion. It's a little more than a time series analysis. Okay. Ultimate aim being identification of critical vulnerabilities in the target system. Collateral damage is a huge issue today. I would like to hit a particular target system at the point where it is vulnerable the most. For example, if my satellite imagery and from that the AI can extract the roadways, the pathways, etc., and have a common funneling point of a bridge, it is the bridge that I would like to target. With this, I come to the end of my presentation. Jahan, thank you for the time.
Hi everyone, this is Aves from Pixel Space Technologies. Thank you for the panelists for being here and for the opportunity as well. So what Pixel is a space technology company, obviously, but we are a space data company. So there's two things there, space and data. We build our own hyperspectral satellites that go into orbit, capture images of the Earth. And then we also build the data analysis tools that are required to actually extract useful information from this imagery. Getting data down is just step one. How can you actually extract useful information from that is the important part. When we started with analyzing existing sources of satellite data that are available around the globe, predominantly multispectral images, panchromatic images, RGB images. But the realization was that spatial resolution only solves one half of the problem. You can see things in a lot more detail, but there are some things that you cannot see no matter how good your resolution is, and you need to be able to see them in a lot of spectral resolution as well. The detail that you are seeing needs to be much higher. But obtaining hyperspectral data globally and especially in India is not something that has been done commercially. There's one hyperspectral satellite that we have, the ISpA satellite that ISRO has launched, limited by the spatial resolution. So the idea was that we will build at Pixel the world's highest resolution hyperspectral satellite constellation, which will also become the world's first commercial hyperspectral satellite constellation. We are doing this at a 5-meter spatial resolution, which is around 6 times better than what has been achieved by HISIS or by other space agencies around the world, which is 30 meters. And we'll be doing this in many hundreds of bands that enable us to see the issues that we actually need to be seeing. The constellation part becomes important because we need to be seeing things in a variety of different geographies, in different areas of interest, and we need to be seeing them, as the other panelists have mentioned, on an almost daily basis, if not less than 24 hours. So we would actually see things when they are needed to be seen, which is where the constellation comes into the picture. What exactly is hyperspectral and what makes it unique? You're able to see things in hundreds of different wavelengths compared to the 3 wavelengths that you're able to see with our eyes. You're only able to see in red, green, and blue. Existing multispectral satellites take that up to 10 or 20. With our hyperspectral satellites, you're able to take that to many hundreds of wavelengths. And the difference that you can see here, you're able to see what is within the water, you're able to see what material the road is made out of, what crops are growing, all in a single image. Coming to defense and intelligence and strategic uses specifically, where hyperspectral helps, as I mentioned, is not in the spatial domain. There are some things that are camouflaged, there are some things that are hidden, there are some things that you are not able to see with normal eyes or normal sensors, which is where hyperspectral actually comes into the picture here. In the images that you see, that red dot there was a specifically camouflaged object that was kept for a test. You're not able to see that in the panchromatic image, regardless of the resolution. You're not able to see that in a multispectral image, but you're able to clearly see that in a hyperspectral image because the chemical composition of that object is different. That's something that cannot be hidden, whether that's specific gases or chemicals that you're looking at, whether that's specific objects that you're looking at, as well as certain underground mines and tests that you're able to see with regards to how the soil and the land has changed above. That's where hyperspectral really shines, and that's what we're attempting to do here. There are many more use cases in terms of what hyperspectral has been able to do. Some of them will require building spectral libraries together with the end users. But it specifically helps in a variety of different border related use cases as well as maritime related use cases. In some cases, as I was mentioning here, dark vessels, you're able to actually look at those vessels and identify the material composition that will give you a lot more information on what kind of vessel that actually is, whether that's commercial, whether that's something else. You're able to look at a particular area and say that this tank here that you're looking at is either camouflage, it's actually real. You should not be wasting your resources here. The good thing about Pixel is that just as of a couple of months ago, we already launched the first demo satellite with 10-meter camera. So we designed a hyperspectral camera, the satellite, and launched it on April 1st, 2022. That's already gone up there. That's already validated and is working healthy today. And we have images also coming down from space, which is the important part. We're actually able to see various different spectra in hundreds of bands. That makes hyperspectral special here. So with the satellite up there, we have validated that the camera design, the satellite design, and our operations are working as they're supposed to. What we are currently up to at Pixel is manufacturing 6 more satellites, which will be the first phase of our constellation that are already in production. That will go up early next year, beam down data, and we're able to, with just 6 satellites, cover various geographies on every 24-hour basis as well, which will provide our nation with a lot of capability to actually look at things when you need it at an almost real-time basis. So I think that said, what we're attempting here is to be able to bring a new kind of capability that has not been present even globally and leapfrog India's technological prowess. The best commercial hyperspectral satellites that have been ever launched were 10-meter satellites by a Chinese company. We have already launched our 10-meter demo satellite as of a couple of months ago, and we're doing 5-meter resolution next year, which will take us to be the world's best commercial hyperspectral resolutions globally. So we are happy to start providing this data already to a bunch of customers. We're working with certain government and private agencies to see the utility of the data as well. So that's it. Thank you again for the opportunity, and we'll see you later.
First of all, it's an absolute pleasure and a privilege to be talking to you today. And I'm Navneet Singh from Kepler Aerospace. We are basically into space-based electronic warfare systems and secure communication networks. So I'll be talking about LN decoding from space, as it has been made quite clear today from various panelists and esteemed members that RF detection and geolocation from space is now a critical juncture in war fighting. I mean, it has been quite apparent in the war that has been going on, whether it be Azerbaijan or whether it be Ukraine. Electronic warfare is now the new domain of warfare that has to be put a lot of emphasis on. And we will have a discussion regarding that. I'll just go over the space-based electronic warfare scenario that's already around and how small satellites can help in this regard. So space-based electronic warfare has been the domain of government agencies. Why? Because they are big, expensive satellites that need to be launched in geostationary orbits for longer station keeping. And usually there are a couple of examples. For example, the EMI sat that was launched by ISRO with association with DRDO, which uses baseline interferometry for geolocation of emitted emitters. Then we have the Orion satellite system, which is an American ILINT system, which is extremely expensive, 100 feet antenna in space in geostationary orbit, very expensive. And then the darling of the OSINT community, the Sentinel-2, free data plus dual use of its own data. Because Sentinel is actually a SAR satellite, but because of the interference patterns that are generated, it's very useful for us. And since raw LN data is extremely hard for private companies to actually acquire, this data is what we use for our initial testing of our algorithms. So first example of free data being utilized for dual use technologies. As you can see, this is an interference pattern being generated in Misrata, Libya. It's an interference pattern being generated by the Coral EW system of the Turkish armed forces that has been stationed there, trying to jam something out in the ocean. Now, you look at it and there's where your data fusion comes into play. You can join this data with AIS data to understand what are you jamming. So the next day, you see what exactly was being jammed. The day before, there was an Italian Horizon-class destroyer roaming around in the same area, transmitting its own onboard marine radar, which was again captured by the interference pattern.
Utilizing that information, utilizing data fusion from AIS, you can come to a wholesome picture without having LNT assets in space. But we should not depend only on ocean communities. Now, coming to the second picture, if you see, that is again data fusion between AIS and free data available. That's the 5 gigahertz interference pattern being generated by a Canadian Halifax-class destroyer. Similarly, now we look at a picture up in the Surjan Mountains in Iran. There is a very particular 5 gigahertz interference pattern being generated on the Sentinel-2 imagery. Why? Because subsequent imagery analysis of the data that has been acquired by, again, Google shows a S-300 surface-to-air missile system in Surjan, Iran. So again, utilizing data, free data sources and data sources already available, you can already get a similar comprehensive picture. But if you see, there is a slight problem with this data. You cannot use this data for targeting purposes. You have a massive interference pattern being generated, giving you a very huge circular error probability of where your target may be. You cannot use it for targeting. That's where data fusion comes into play. So for example, let us again see an interference pattern. I'm so sorry about this. It's just the open source intelligence data that we have. Here you can see another 5 gigahertz interference pattern being generated in Fuzhou, China. Seems interesting. By 5 gigahertz, we know that it's an air defense radar. But how do we pinpoint the source of information? We go to Google Maps, we check out what is in that general area of interest. And then we see there is a radome, which it's an X-band, C-band, X-band air defense radar. So utilizing that and creating a wholesome data picture, you can come to an actionable amount of data, actionable intelligence based on open source. But having your own assets and having a geolocation capability with cluster satellites adds on to that data. So as you can see, this is the basic philosophy of what multilateration in single passes, multiple passes, and data fusion brings to the table. You bring down the circular error probability down to an actionable level, where even if your initial sensor does not have the capability to give you the right amount of accuracy, by utilizing fusion, you can get it down to an actionable level of quality. So right now, if we see the threat scenario around us, I mean, the main Pakistani air defense radar is a TPS-77 American-made radar. Plus, they just now acquired some Chinese radars like the JY-27A, which is an anti-stealth UHF radar. And it has been posted in Mian Valley. And so these are the kind of radar systems that are either mobile or non-mobile. And I'm not even going into the maritime domain where you have a ship moving around everywhere. So radar fingerprinting and actually being able to geolocalize RF signatures is an eminent domain that has to be focused on. And I'm very glad that almost all of the panelists have put focus on data fusion, sensor fusion, and electronic warfare from space. So again, thanks to our friends at Hawkeye and Planet Labs. This was the data that was generated by them during the Galwan Valley incident. As you can see, multiple circular error probability ellipses were generated for the RF data. And utilizing the data from Planet Labs, they were able to geolocate it to a much smaller size than what is actually possible from RF LNT systems in space. Two pictures that I would like to show you, again, as our Navy panelists have brought it out, dark ship recognition and AIS, non-AIS recognition ship detection, which is a very crucial part of maritime self-awareness in today's world. If you see these two pictures, the picture on your left is a study by the Naval Postgraduate School, US, where it shows the number of receivers that you have. The greater number of receivers, the better your location accuracy. Why I bought that picture, I'll tell you in a moment. But having more expensive satellites in space doing LNT is nice. Having numerous satellites doing LNT in space is better. The higher the number of receivers, the better your geolocation is. So that's what that picture is all about. And the other picture is basically the scenario where what does AIS show you and what it does not. What AIS shows you is in blue. What it does not is in orange. That's a huge disparity, especially with the roving Chinese fleets that are roaming around in endangered Earth oceans, fishing to their heart's content. Everybody has their AIS off. How do you detect that? So now coming to what Kepler has been up to, we are a space electronic warfare company, and one of our primary systems that we have been working on is called Citadel Space-Based Persistent Surveillance Network System, which is a cluster of 4 satellites flying in a formation. And we, again, as it has been said, again, co-located sensors give you better accuracy on ground. So we work with EW and EO clusters together, where we have 3 EW satellites and 1 EO satellite flying in the same formation with joint taskings and intelligent taskings, where emitters of interest are automatically sent as a tasking to the EO satellite in the cluster over our inter-satellite network, and the imagery can be acquired at a much faster speed and giving you a much shorter OODA loop. Our geolocation platforms right now are working on TDOA, FDO analysis, with the RF baseline being given by the distance between the 2 satellites in the formation. We have certain numbers regarding the geolocation accuracy that has been given. Again, these numbers are preliminary, and we are working on reducing the CEP by utilizing data fusion networks. So another important factor when it comes to small satellites is small satellites are very nice. They're small satellites, they're cheap, small capital cost, and people talk of them as if they have the same capability as bigger satellites. Honestly, they do not, which we agree. There are certain, you can't have everything. Some compromises are there. So how do you move around that compromise and make sure that your smaller satellites are giving you the same quality of data that your bigger satellites are giving? I mean, you can't equate a 1700 crore Cartosat and a 30 crore 60 new satellite. That is absolutely impossible to. But that's where tipping and queuing comes into place. Tipping and queuing basically means you use sensors with low fidelity to tip and queue your bigger sensors with higher fidelity to the actual area of interest. That's where what we have been working on. For example, our EW satellite has a huge on-ground footprint of, let's say, 1200 kilometers square. And your CEP will be about 200 to 300 meters with geolocation with 3 satellites. How do you bring it down to an actionable source of intelligence? You utilize the EO satellite as your determinant, as your queue, to ensure that you can get a higher fidelity or data with the same smaller satellite system. So, for example, and then comes the capital acquisition cost. Everybody wants the best, but nobody wants to pay for it. So how do we go ahead? We do in a tiered system. We can give lower capability, more satellites, higher capability, less number of satellites, but with varying amount of what we can do for you. For example, the smallest option that we give is a 5 kg satellite. It's a 3U satellite. Everybody knows small satellite. It can be launched immediately. But the amount of frequency coverage and the IF coverage. IF is basically your instantaneous frequency coverage, which is very important when you're trying to radar fingerprint something with a high PRF and PRI. Sorry. So to ensure that you can meet such requirements, you need a higher frequency coverage, IF frequency coverage. So our smaller satellites have a lower IF coverage and lower number of frequency bands being covered. Again, the frequency bands are a factor of satellite real estate. You need to put specific antennas to target specific frequencies. Yes, you can put a very wideband antenna, but your gain is very low, and you need high gain for EW systems. So real estate, power, and mass. Again, as it has been bought out again and again, people are looking for shortened OODA loops. People are looking for immediate data acquisition and process data. They don't want to, you download the data, I'll do it later. So that's why you need to have edge compute, which we have on our satellites, to do computation of determinant solutions. So we are not just downloading IF data and RF data, which is huge amount of data anyways. What we are saying is we are doing determinant solutions on board the satellites to give you immediate actionable intelligence on the ground. So for that to happen, it requires power. You need power to actually do computation. So for that, our satellites, because of the mass and power requirements for different levels of satellites and different masses of satellite, we have different levels of accuracies on the ground and different level of features. As I said, we have a co-located EO sensor along with our EW cluster. So again, the cluster EO sensor is defined by the aperture size being given by the satellite size. So because of that, we have different sizes of 4 meters, 3.5 and 1.4 meters, GSD on ground at 505 kilometers. All our satellite data links are high-speed data links with highly secure networks. They are right now we are actually doing ground control systems for ISRO for their INS series of satellites. So all our networks are completely, I would say quantum, but low-level quantum type encryption protection. Yes, sir. Yeah, almost done. Yeah. So basically, this is now the final slide that I would like to show you. What I'm talking about: formation flying, inter-satellite links, clustered approach to meeting the requirements that have been put forth and meeting them in a substantial way with smaller satellites and giving them as a complement to bigger satellites. We cannot replace big satellites. That is the reality of life. But we can always complement bigger satellites and ensure that the data that you get is almost on the similar footing at a much lower cost. Thank you.
My name is Aaron Wyand. I am from Maxar Technologies, where I'm a product manager. And in the interest of time, I'm just going to show some pretty pictures and show you where Maxar shines, especially since my co-panelists have done such a good job of setting up, the important parts of space-based reconnaissance for decision-making and targeting. There we go. So if you're not familiar with Maxar, we are a global company. We have a presence here in India as well as all over the world, but we are headquartered in the United States in Colorado and are a major commercial satellite provider to the US government as well. So my co-panelists, like I said, have already talked about resolution, accuracy, swath width, and latency as the important elements of decision-making using geospatial information. So just starting off with resolution, we see how you can move from just being able to identify aircraft on a landing strip or at an airport to identifying specific, fuel tanks and weapon systems using 30 centimeter resolution imagery. So currently we do have WorldView 3 at 30 centimeter, and with WorldView Legion launching later this year, we are going to triple our 30 centimeter class resolution capacity over the next few months. So moving from resolution to accuracy, so that's our ability to precisely position something on the Earth's surface. Our commercial constellation is capable of getting down below 5 meter accuracy. And with our emerging and maturing precision 3D capabilities, we're able to bring that down even lower to 3 and 2 meter accuracy across the constellation. And then I really like the mention of swath width earlier. This really shows where we shine. So when we're able to collect at a low, a 30 centimeter or 50 centimeter native resolution over wide areas, that really opens up your opportunities for discovering new things. Even if you're focused on one target, you're collecting a lot more. So in the lower left, we show that with the launch of Legion, which is a highly agile payload, we'll be able to image all of Taiwan in a single pass at 50 centimeters. So that's pretty cool. So where we're at today, we have our 4 in orbit. Our archive is over 125 petabytes of archived imagery, going all the way back to '99 with Iconos, the first high resolution commercial imaging satellite, and then moving all the way to this year with the launch of WorldView Legion, which is really going to increase our capacity. We're going to be moving from today at 3.8 million square kilometers per day collected to over 5 million square kilometers every day. So this really shows off a lot of what I just talked about in terms of accuracy, resolution, and 3D. So this is a video fly through of imagery that we collected in February of a Russian convoy outside of Kyiv. It extended over 60 kilometers. So what we did was took the 2 images that we collected, pinned them to the 3D mesh, and then recorded a fly through. In the interest of latency, this was all done within 24 hours of imagery collection. So pretty awesome. That runs for another minute. If you want to see the whole thing, come by the Maxar desk. So in terms of what I provide, so I'm an access product manager. Internationally, we provide a number of access services. This allows our international customers to lease time on our satellites, either directly through a direct access facility, virtually through a rapid access program, or tactically, which is my product, the tactical access program, which is a mobile, transportable, direct downlink terminal that moves with troops. So I won't spend too many too much on these slides, but the Direct Access program is our flagship program. This delivers a fixed ground station to the customer. You have encrypted and sovereign control over your tasking, uplink and downlink, and you'll have imagery in hand in minutes. And you're able to submit your tasking to the satellite up to 15 minutes prior to the collection. Rapid Access gives you the same basic tasking and delivery mechanisms, but without the fixed ground station. So you do everything virtually through a web-based application. Very similar timelines. It's just that we handle the tasking uplink and downlink through our ground station. And then finally, my program, the Tactical Access program, is designed to give tactical users in the field in denied and contested communications environments direct downlink capability over X-band, and in a form factor that moves with troops, that can be checked as airline luggage, can be set up by 2 trained users in under an hour, and then move when it needs to. So that's all I have. I'm sorry I had to go super quick, but I want you all to get to lunch on time, so thank you.
Keeping the time constraints in mind, I'll just have 1 or 2 questions. The first question is to Oves. First of all, congratulations on your satellite going up, and it is a matter of great pride for us that we'll have the best resolution hyperspectral, which in my own admin days, we used to just dream. We used to talk about JPL libraries and all. So let me ask you, the kind of product that you have, it requires a very intense involvement with the user. How would you describe this journey to be? And from a person who's providing this capability, how would you want the forces, the defense forces, to engage with you? Because this needs to be started from an inception stage. It cannot be that it can be done at a later stage, because it is very time intensive and man hour intensive. Your comments?
Yeah, no, thank you for that. I think it's very timely question as well. We just launched the satellite. The commissioning is almost at the end stages, and we are bringing down imagery very regularly. The thing with hyperspectral data is you can only reach its complete capability once you have a spectral signature library for you to be able to look at and say, yes, this is exactly what we are looking at. And what we are doing this year until we put up our constellation is to be able to create these pilot access programs where we closely work with the end customers, and we're already doing with a few private organizations where we identify certain areas of interest. We take images from the satellite, and then we sit down together with the end user and say, this is what you need to be looking for. This is what you've asked us to look for. Let's go out and create this library so that once the regular operations come into being, we can actually get moving without having to waste any time. Certain things will have to be done specifically with the end user, especially with strategic forces, because the materials that might be used for things that you're trying to detect, or the chemicals that you're trying to detect, or the gases you're trying to detect, will not be available in public libraries. For agriculture, yes, you'll have it. For minerals, you'll have it. So what's needed is to be able to actually create some sort of a formalized program with different agencies who will have different use cases, for us to be able to actually sit down where we can actually take images, sit down together, identify what needs to be created, whether we need to take separate images that we are creating from drone cameras or through the satellites themselves, and do that. So working closely between now and when the constellation actually goes up will save that bit of time, so we can start serving commercially and get to that capability quicker.
Thank you. Ekumno Baduni, sir, as Commandant DIPAC, you have the repository of all the data that comes to you from various sources. Now, I'm given to understand that you have been supporting industry in development of, say, AI algorithms and some kind of process automation. Since a lot of our industry members are present here, how would you like to, any message that you would like to give as to how the industry can engage with you and what support they can expect from you to develop technologies that would be relevant for future warfare? And especially like programs like the hyperspectral program, which require a very intensive industry user interfacing.
Okay, I'll answer the part of the question, how much support, the one word answer, full support. not a problem. We are there to find solutions in national interest, and therefore there is no point in me saying that we will not provide you full support. The things that we are looking from industry, most of the parts I had covered in my presentation itself. In specific, the collaboration part is of critical importance. Uh, Industry should stop looking at defense forces merely as an end user or a product buyer. You got to, at this interim phase, look at us as a product development partner itself. Uh, Pixel had bought out, the hyperspectral is a very, very promising technology. It is yet to mature to a level which has its military applications. However, it is moving very fast and it is the niche technology. So multiple agencies, even within the private establishment, trying to do their independent job, will not yield the speed of results. It will yield results, but not the speed of results, because you have certain amount of knowledge that we simply do not have, and there is a certain amount of knowledge we have that would be beneficial to you in your product development. The last thing I would say to the industry is something that had been covered by AVM Ranade also: patience. Everybody is looking for a quick fire profit. If you are looking for that, you are at the wrong end of the business segment. That is with defense. You got to be very clear in your mind that defense always looks for niche cutting edge technologies. The word cutting edge, by its very connotation, means that there is no product available for you to describe or to buy off the shelf. It has to be something that has to be developed, and all developmental aspects in technology have their own gestation periods. And this is what you have to live through. So do not get frustrated and tired too fast down the chain. Thank you.
Thank you, sir. In interest of time and approaching lunch, we need to push in one more session. So may I just thank all our panel members. May I please request our DG to just give the gifts to the panel members, sir.